Welcome to the Deep Dive. Today, we're tackling something I think many of you listening have probably run into. Really pushing the limits of precision in manufacturing. You know, maybe you've been frustrated by tool chatter in CNC,
Oh, yeah.
leaving a surface that's just not quite right. Or maybe you've seen a really tough, hardened part warp slightly after you thought you'd finished machining it.
Happens all the time. We're just hitting a wall trying to get those really tiny, complex internal shapes.
Exactly. With conventional CNC, you're always sort of battling the physical limits,
Mhm.
right? The tool, the material itself. Hardness especially can be a massive roadblock. You get tool wear, issues with dimensions.
Absolutely. And that's where, this other technology, electrical discharge machining or EDM comes in. It uses a completely different approach.
And the key thing, the reason it offers such amazing precision is, well, it shapes metal without actually touching it physically.
That non-contact part is the absolute game changer.
Yeah.
Instead of like a cutting tool literally carving away material, EDM uses these incredibly controlled electrical sparks, tiny sparks, eroding the material.
Which just opens up totally new possibilities
Mm-hmm.
for accuracy, for working with materials that are just, well, incredibly difficult otherwise.
Mm-hmm.
So we've looked into some really interesting sources explaining why EDM works so well. And our mission today in this deep dive is to really understand how it gets that precision and, figure out when it's clearly the best tool for the job.
Okay.
All right, so let's start with those super hard materials. The kind that make even really good CNC tools just struggle. Why does EDM seem to handle them almost easily?
Right. Well, think about trying to machine something that's, say, harder than HRC50. Rockwell C50, that's pretty hard.
Yeah.
With a standard CNC process, you're probably going to see your cutting tools wear out really fast, like alarmingly fast. Your surface finish probably won't be great, and holding tight tolerances, that becomes a real challenge. Leads to delays, cost overruns, all that stuff.
Yeah, we've all been there, unfortunately.
Okay.
But then you switch to EDM, using these electrical discharges to erode the material. And the sources we're looking at say it can handle materials at HRC 60, 70, even higher.
Absolutely.
Right.
Higher. And it does it without wearing out a tool in the traditional sense, maintaining accuracy, and giving you these really nice surface finishes.
What's the fundamental difference there?
It goes back to that core idea. No physical contact. You see, CNC relies on the cutting tool being physically harder than the workpiece. It has to be to cut it.
Makes sense.
EDM, though, uses these tiny controlled sparks. Each spark generates this intense, very localized heat. We're talking thousands of degrees, but in a microscopic spot.
Wow.
And that heat vaporizes a tiny, tiny bit of the material. Because it's not pushing against the material's hardness, well, basically doesn't matter. As long as it conducts electricity, EDM can work on it.
So it's less like carving stone and more like, I don't know, using a microscopic lightning bolt to precisely vaporize bits away.
That's actually a pretty good way to think about it, yeah. Because it doesn't rely on brute force, EDM can process these incredibly hard alloys. Think tool steels, tungsten carbides, those fancy aerospace superalloys.
Things that would just chew up a conventional tool.
Exactly. EDM machines them without the tool dulling or breaking because electrical discharge is doing all the work at that tiny scale.
Okay, this is where it gets really interesting for me. This whole no physical contact thing.
Yeah.
The sources emphasize that this eliminates mechanical stresses. What does that actually mean during machining? What are the benefits?
Oh, it's huge. It creates a cascade of advantages. First off, no physical cutting force means no tool deflection. The tool bending slightly under pressure.
Right, which throws off your accuracy.
Precisely. And no vibration, another big source of error in CNC. The workpiece itself is also much less likely to shift or distort because nothing is pushing on it. And like we said, no friction means hardly any tool wear in the conventional sense. Plus, you don't get that big heat buildup you sometimes see at the cutting edge with CNC because there's no rubbing.
Right, it's like trying to, perform delicate surgery versus just forcing your way through. You're going to get a cleaner cut without the force.
That's a great analogy. And yes, EDM does generate heat where the spark hits, but it's incredibly localized, just a tiny microscopic zone.
Okay.
And that dielectric fluid, the special liquid bath the process happens in, is key here. It acts as an insulator, preventing a discharge until the voltage is just right, and then, crucially, it flushes away the vaporized particles and cools that tiny spot immediately.
Ah, so the part itself doesn't really heat up overall.
Exactly. It prevents any significant temperature rise in the bulk of the material.
And this super controlled removal, this vaporization,
Yeah.
that's what lets EDM get those incredible surface finishes the sources talk about. Like Raw 0.1 micrometers. That sounds ridiculously smooth.
It is exceptionally smooth, almost mirror-like, and achieving that kind of finish directly is a massive advantage.
Why? What's the practical benefit?
Well, in some fields, like medical implants or optics, that smoothness is absolutely critical for function or, biocompatibility.
Okay.
In other cases, a smoother surface reduces friction, maybe improves sealing, helps fluids flow better. Plus, getting that finished directly often means you can skip secondary steps like grinding or polishing.
Which saves time and potentially avoids introducing inaccuracies during those extra steps.
Exactly. Especially polishing complex internal shapes by hand that's difficult and not always perfectly consistent.
It also sounds like this non-contact approach opens up some really cool design possibilities. The sources mention complex shapes, sharp internal corners, deep, narrow slots, things that are tough or impossible with a spinning cutter.
Definitely. Think about making a mold for a really intricate plastic part. Maybe it needs truly sharp inside corners.
Which a round milling tool can't make.
Right, always leaves a radius. But with wire EDM, you're using this incredibly thin wire, sometimes thinner than a human hair, as the electrode. It can cut perfectly sharp internal corners.
Nice.
And with sinker EDM, you machine an electrode, usually graphite or copper, into the exact shape of the cavity you want, sharp corners and all. Then you sink that electrode into the workpiece.
So you can create really complex 3D cavities.
Absolutely. Things a rotating tool just couldn't physically reach or form. Imagine a really deep, thin rib or a narrow slot with perfectly parallel walls. Trying that with a long, thin milling tool. Big risk of deflection or breakage. EDM handles it easily.
Okay, so EDM is clearly the winner for super hard materials and these really intricate shapes. Let's pivot slightly to another critical area, making high-precision molds. Why is EDM so often the go-to method there, maybe over CNC?
Yeah, molds are a perfect example. Mold making really pushes the limits. You need complex internal shapes, often very deep features, maybe intricate channels for cooling. And molds are almost always made from hardened tool steel, so they last a long time. CNC can struggle with all of that, the depth, the complexity, definitely the hardness. You might have to compromise the mold design.
And a compromised mold means compromised parts, potentially lower quality, shorter mold life.
Not good.
Not good at all. So the sources are saying EDM shines here because it can create those complex internal shapes, those sharp corners, deep cavities that a cutting tool just physically can't reach sometimes.
Exactly. And because there's no physical force, you don't risk distorting delicate features, like maybe thin walls between cavities in the mold.
Right. Let's go back to those sharp corners for a second. With sinker EDM, you make the electrode the inverse shape, sharp corners included.
Precisely. And with wire EDM, like we said, that sharpness is limited only by the wire diameter. We're talking maybe 0.02 millimeters. Incredible detail, crucial for how the final plastic part looks and functions.
And this precision carries through to the overall size too, right? The sources mention tolerances like plus or minus 2/10,000ths of an inch, 0.00002 inches, or 0.005 millimeters. That's incredibly tight.
It is, and absolutely critical for molds. You need that accuracy so the molded parts fit together perfectly. Maintaining those tolerances consistently, especially in hardened steel, is where EDM really excels.
What about deep cavities or features that are just hard to physically get a tool into?
Yeah, another strong point. For sinker EDM, you can design the electrode to be long and thin to reach deep down.
Oh, okay.
And wire EDM cuts right through the material thickness, however deep it needs to be, maintaining accuracy all the way down because the wire isn't deflecting like a long milling tool would.
Okay, we touched on this, but it seems really critical for molds. Machining the hardened steel after heat treatment, that avoids distortion headaches.
It's a massive advantage, a game changer, really. Traditionally, you might machine the mold parts when they're softer, easier to cut. Then you heat treat them to get the required hardness. But that heating and cooling process, it can cause the steel to warp or distort, just slightly.
Even if it was perfectly machined before.
Exactly. So then you might need more machining on the already hardened steel to correct it, which is difficult, slow, hard on tools, and might still not be perfectly accurate.
Sounds frustrating.
It can be. EDM lets you flip that. You heat treat the steel first, get it fully hardened and stable. Then you use EDM for the final precision features. Since EDM doesn't induce stress or much heat, it avoids those distortion problems.
So you machine the final precise shape into already stable hardened material.
Precisely. It simplifies everything and guarantees the final dimensions are accurate in the hardened state.
And that must help the surface finish inside the mold too. which affects how the plastic part releases.
Absolutely. EDM can produce very smooth finishes inside the mold cavity, often around 5 RMS, maybe 4 microinches raw. That helps parts release cleanly, reduces wear, and again, often cuts down or eliminates the need for manual polishing inside complex cavities.
The sources even mention EDM enabling complex cooling channels, like conformal cooling.
Yes, that's a big one for productivity and part quality. Traditional cooling channels are just straight drilled holes.
Right.
EDM allows you to create cooling channels that actually follow the shape, the contours of the mold cavity itself.
Oh, interesting.
This cools the plastic much more easily and efficiently. You can often run the molding machine faster, get better parts with less warpage. It's a significant benefit.
And you can even create textures or tiny features directly.
Yeah, with sinker EDM, you can machine a texture onto the electrode and it will burn that texture right into the mold surface, or create microscopic features for specific functions. And the repeatability is fantastic, essential for making multiple identical mold cavities or replacements.
Okay, it's really clear why EDM is such a powerhouse for molds. Let's dig into the fundamental differences again. What are the key limitations of CNC that EDM just sidesteps with its burning approach?
Well, the sources really lay it out. When you rely on a physical tool-cutting material, you hit certain inherent limits, especially with hardness, complex shapes, or extreme precision needs.
Right, you often have to compromise the design or use multiple setups, which adds risk.
Exactly. EDM, using those controlled sparks, just bypasses a lot of those limits.
The sources had that comparison table. Let's walk through some key points. Material hardness.
Yeah.
CNC is limited by its tool's hardness.
Absolutely. Tool wears out, breaks, finish suffers if the workpiece is too hard. EDM doesn't care about hardness, essentially, as long as it conducts electricity.
Internal corners. CNC leaves a radius because the tool spins.
Wire EDM can give you perfectly sharp internal corners. Huge difference for some designs.
Mechanical forces. CNC pushes on the part, causing potential deflection, vibration.
Right. EDM is non-contact, no mechanical stress, much better for delicate parts or features.
Multiple setups. CNC might need several setups for complex parts, risking misalignment each time.
Yeah, every time you reclamp the part, there's a chance for tiny errors to creep in. EDM can often do complex 3D features in one go, maintaining better relationships between features.
Tool wear. CNC tools wear down, affecting accuracy over a run.
Yep. Wire EDM uses fresh wire constantly. Sinker EDM has predictable electrode wear that the machine can compensate for automatically, so accuracy stays consistent.
Heat generation. CNC can generate significant localized heat from friction.
Which can cause issues. EDM's heat is super localized at the spark, and the dielectric fluid cools everything efficiently. No significant heat buildup in the part.
And finally, micromachining, making tiny features.
CNC struggles with tiny tools. Vibration becomes a big problem. EDM, especially wire EDM, excels at microscopic details.
So those CNC limitations, tool dulling, inconsistent cuts, deflection EDM, just avoids them.
Pretty much. You get sharp corners with wire EDM. You replicate complex electrode shapes with sinker EDM. You don't worry as much about depth-to-width ratios, no workpiece deflection. It just opens up possibilities for complex, delicate, precise features that are really hard otherwise.
Okay, we've got the hard materials, the complex shapes, but there's that other angle the sources mentioned. How EDM can actually get rid of some major heat treatment problems while keeping the precision.
Yes, this is really quite clever and a major practical advantage. Think about the usual process. You machine a part close to size when it's relatively soft.
Easier to cut.
Right. Then you send it for heat treatment to get the hardness or strength you need. But the heat treatment itself, the heating and cooling, it often causes the part to distort. Just a little bit, maybe, but enough to lose that initial precision.
So frustrating. You get it perfect, then the hardening messes it up slightly.
Exactly. And then you have to do more machining, maybe grinding on the now very hard material to try and get that precision back. It's difficult, expensive, and might not even be fully possible depending on the shape.
So how does EDM break that cycle?
By changing the order. Because EDM doesn't care about hardness, you can do the full heat treatment first. Get the material to its final, stable, hardened state, and then you use EDM to machine the final precise features. Since EDM doesn't introduce significant stress or overall heat, it doesn't cause distortion like machining does after heat treatment.
So the sources had that other table comparing the sequences. Traditional is CNC, then heat treat, then more finishing. EDM allows heat treat, then EDM for the final precision.
Precisely. It tackles the distortion issue head on. You're not trying to fix warping after the fact. You're creating your final shapes in a material that's already stable and hard.
Which must be more accurate.
Much more predictable and accurate. And you avoid the difficulty of trying to machine hardened steel with conventional tools for those final touches. EDM handles the hardened material without the tool wear issues.
Seems like it would simplify the whole process, too. Fewer steps, maybe? Faster overall?
Often, yes. Fewer steps, less risk of errors introduced during intermediate finishing. And the real win is the final precision. You're achieving it after the part is stable, so it holds that accuracy.
But wait, EDM uses heat, those sparks. Doesn't that affect the heat treatment?
That's a good question, but the heat from the spark is so localized, literally just a few microns deep, that it doesn't really affect the bulk material properties established by the heat treatment. The core hardness and structure remain intact.
Okay, so it's a surface effect only, basics.
A very, very shallow surface effect, yes. It simplifies planning immensely because you don't have to guess how much a part might distort during heat treat and try to compensate beforehand. You machine to the final print dimensions in the hardened state.
Huge for molds and dies, I imagine, where that final precision needs to last.
Absolutely essential. And for any complex part with lots of critical features, being able to machine them accurately after hardening is just invaluable. Sometimes it's the only way to achieve the required tolerances.
Okay, so let's try and nail it down. The superior precision of EDM really comes from, well, a combination of things, doesn't it?
It does.
First, getting rid of those physical cutting forces, no deflection, no vibration. Second, its amazing ability to handle super hard materials without breaking a sweat. Third, creating those incredibly sharp internal corners that you just can't get with milling. And fourth, that crucial trick of maintaining dimensional stability by often machining after heat treatment.
That sums it up perfectly. When the stakes are high, when you need absolute precision, especially with tough materials, complex shapes, or avoiding heat treat distortion, EDM isn't just another option. It's often the clear, definitive solution, sometimes the only solution.
This has been incredibly insightful, really clarified things for me. And it does make you wonder, doesn't it? If you can precisely shape pretty much any conductive material, no matter how tough it is, what completely new designs or engineering possibilities does that unlock that maybe we haven't even fully considered yet?
That's a great question to ponder. The possibilities are vast.
Definitely something to think about. Thanks for diving deep with us today.